Hi there, welcome to Systems with Two Variables. So this video is technically a review from Algebra 1, but I wanted to go over it because we're going to need it here in Algebra 2. So the first thing we're going to take a look at as a refresher is just determining how many solutions we have in our system. So on this first one, I see there's this extra 3 next to the x, and I can see that this one is kind of by itself. So what I'm going to do on the top one is I'm going to divide everything by 3. So now those are going to cancel out. And then this one I'm just going to kind of leave as is because now I can see that these are exactly the same line. Well, if I tried to graph both of them, it would look something like this. I would have 2 lines overlapping and they would cross in many, many places. So in this case, for this system, I would have infinitely many solutions, or I would have coincident lines. I like to say coincident because it's a coincidence those lines are the same. So that means they cross many times, so really any combination of x and y is going to work for both of them. This next one, I can see that this one has y all by itself, so I'm just going to leave it as is. This one, y is almost by itself, except I need to move a couple of things over, like this 5x. I can subtract from both sides, and then you can see I divided everything by 2, and I literally mean everything. So here's 5 over negative 2, negative 8 over 2. So these two, let's compare these. Okay, so it looks like they're both going down 5 over 2 and moving that way. But it looks like here in yellow that they're beginning in 2 different places. The top one is beginning at 11 and the bottom one is beginning at negative 4. So these, when I try to graph it, is going to look something like this, where these lines are going to move the same way, down 5 over 2, down 5 over 2, but they're going to begin in different places. So because these lines are parallel, they never ever cross, so I would have no solutions. There is no combination of x and y that is going to work. On this last one, these lines look completely different, but I'm actually going to try to do a little bit of solving to see what happens. So first things first, I'm going to move that 3x by subtracting it to the other side. And then I'm going to divide everything by negative 7. And again, I do mean everything. So negative 3 over negative 7. So here's positive 9 divided by negative 7. And then I can do the same thing on this one. So I'm going to move this 2x to the other side. And you'll see that little pink highlighter to show you where I got that negative 1 over 2. So here's 2 divided by negative 4, negative 1 over 2. Well, these lines are completely different. They are moving in different ways, and they're beginning at different places. So when this one is graphed, it's going to look something like this. So these are only going to cross each other one time. So this would be one solution only. There's only one combination of x and y that's going to work. So that's kind of where we're going to kick things off, is solving by graphing. So here we have Nahom graphed the following lines. Help him find the solution so he doesn't have to solve it algebraically. So again, we have 2 different equations, and we're trying to find a solution, which is where we have an x and a y. So that means we just look where the lines cross. So this one happens to have one solution, and it's at 0, 3. So I could plug that in, and it works for both. Plug in for both. All right, we're going to try one more, which is going to be an inequality. And so all of these I want to talk about is how these got created. So in this first one, I can see that y is greater than, and it's not equal to. So if it's greater than, I'm going to shade above. And then I can see that I began at positive 2. So here's positive 2. And you'll see that I went down 2 over 1. So that's how this one was graphed. And you'll see it's a nice dashed line because I'm not equal to. Okay, let's look at the bottom one. So I have y is less than, which means I'm going to shade below. And it looks like I can be equal to, so I've got a nice solid line. And then this one was beginning at negative 4, and it's going up 1 over 1, up 1 over 1, up 1 over 1. So on here, when I pick solutions for this type of system, because of the shading, again, my plan is to look for solutions that work for both. So for this one, that could be this point right here, 5, -2. That's a possible solution. So again, I could plug that into here and it would work. I could plug it into here and that would work. That's what it means by a system. So anything where I see some overlap, lots and lots and lots of solutions. The tricky one is this solution because it does technically pop on both lines, but here's the tricky part. This blue line says I can be equal to, so that's kind of right here. But the red one says I can't be equal to because I'm dotted. So this type of solution, so the one that's at 2, -2, that one would not work because I'm not equal to. So it only worked for one of them and not both. So we have to be pretty picky when we do inequalities. So let's take a look at how we can do other ones algebraically, like substitution. So with substitution, you usually want to pick one of the equations to solve for. So this one, it looks like y is almost by itself. So first things first, I'm going to do a little bit of solving, and I'm going to subtract this 9x from both sides. So I'm going to move this over to both sides. So now I have something that says y equals -9x minus 1. Okay, so usually with substitution, I would take this and plug it in for y at the very top. But I think that's a little bit hard to do because one, I see a lot of fractions. So I'm also going to color that so it's a little bit easier to see. So what I'm actually going to do is try to clear these fractions just so it's a lot easier for me to work with. Well, for starters, I can see that I am dividing by 3 and I'm dividing by 3. So here's what I'm going to do. I'm going to multiply that top equation, everything by a 3. And the nice thing is, math says, thank goodness, that as long as I do it to both sides, I'm in the clear. So I'm going to multiply both sides by a 3 because I want to try to get rid of this fraction, okay? So I'm going to multiply by 3. So those cancel out, giving me regular 2x. Same thing, I'm going to multiply in here. I'm going to cross off the 3's again. So I have positive y. And then I have equal to 6. Well, that's a whole lot friendlier. So now I'm going to do the substitution game. So wherever I see a y, I'm going to plug in what I just did up at the top. So 2x plus, so I'm going to plug this in, so minus 9x minus 1 equals to 6. And now I'm going to go ahead and combine some like terms together. So I have 2x minus 9x, so negative 7x minus 1. Oh, look how much friendlier that is. All right, I'm going to go ahead and add 1 to the other side, giving me positive 7. And it looks like I've already found one piece of my equation. That happens to be x equals negative 1. All right, well, with systems, I need a coordinate. I need to find an x and a y that work for both. Well, here's the good news. I already solved for y up here. So for that fourth step, make sure you find the other variables. I'm going to draw this. I'm going to bring it down here. So I've got y equals negative 9. And now I can actually plug in for x. So here's going to be negative 1. And now I can solve for y. So here's positive 9. We have minus 1. So positive 9, there we are, minus 1. So I've got y is equal to 8. So I've got two things here. So final answer, go ahead and bring them together, and I'm going to write it as a coordinate. So negative 1, comma 8. And that's a point. It works for both. And I could plug it in here, and I would see that it works. So that is my solution. All right, go ahead and pause the video and try number 7 on your own. Welcome back. So again, substitution, it looks like I'm going to try to solve 1 for y equals. So I went ahead and picked this one to solve for y. So it looks like I'm going to go ahead and subtract the 2 onto both sides. So it looks like I have something that looks like this. So now I'm going to go ahead and plug that in to this equation up here. So I'm going to go ahead and substitute and replace and try to clean everything up that I possibly can. Ooh, and I get something that says -2 equals 3. Well, because that's false, I'm going to have no solution. So that's what a no solution is going to look like. So if I tried to graph these, I would get something that looks like parallel lines. They would never cross. So false, no solution on that example. All right, the other way that we can solve is something called elimination. So elimination is going to be nice because your job is to eliminate one of the variables. This is also called linear combination. You'll see that word a lot too, linear combination, because you're trying to combine lines together in a way. So linear combination is another key word that you'll see. All right, so with elimination, your job is to try to eliminate a letter. So it doesn't really matter which one we go with. I'm going to try to eliminate the y's somehow. So the problem is right now, if I tried to add these as is, I would have 4 minus 3, and I would have 5. Well, nothing got eliminated, so that's not going to work. So what I'm going to do is try to multiply the top by a number and multiply the bottom by a number to see if that can help me eliminate anything. So what I'm going to do is I'm going to try doing a little tradesies. So I'm going to multiply everything on the top by 3. So again, everything on the top by 3. So I have 15x, positive 12y, positive 18. Here, I'm going to try to multiply everything here by 4. So you'll kind of notice I switched these numbers around. So again, everything gets multiplied all the way across. So here's minus 8x, minus 12y, and minus 4. All right, so now I'm going to try to combine these together to see what happens. Oh, y's are gone, and it looks like I have something that says 15 minus 8. So here's 7x. And I have 18 minus 4 is 14. So it looks like that worked out really well. X is equal to 2. Not too bad. All right, again, I can't stop. I found one number, so now I have to plug back in so I can find the other one. So I'm just going to pick one of these to plug into. Doesn't matter which one, as long as I use one of them. So I'm going to plug into the original. Equals 6. So I'm going to plug in 2 for x. And my job is to solve for the y. So I'm going to leave it as a y. All right, so here's 10 right here. And I have plus 4y. And okay, that's a whole lot nicer than it used to be. And then I've got it equal to 6. All right, not too bad. Move a couple numbers over. Subtract 10, keep things nice and balanced. So I've got 4y here, negative 4, final answer. Y should be -1. -1. All right, just make sure to write that final coordinate. So I've got x is 2, y -1. Final answer, that is using elimination. So try to eliminate a variable and then plug back in to find the other one. All right, go ahead and try number 9, pause the video and see how far you get. All right, welcome back. So on number 9, hopefully you saw something a little interesting, a little spooky as it were. So I went ahead and took the top one and multiplied everything by 2 because I noticed that the y was a positive 4. Well, to make them match, I just needed to multiply that by 2. So you'll see that part in purple. So I get something that looks like that. So I've got 6x, 4y, positive 10, because again, this got distributed. And then I just moved this equation right underneath it, and I combined them up together, and oh, everything canceled out. So I got something that says 0 equals 0, which is a true statement. So in this case, we're going to have infinitely many solutions. So it's going to always be true. So any number I plug in, any combination of x and y, it's going to work out really, really nicely. See, not too bad, because it's the exact same line. Not too bad. All right, pause the video and try this one using either method, elimination or substitution. All right, welcome back. I'm going to show you both methods, so depending on what you picked. The key on this one is this last step. So whenever you got done, you had to plug back and find y minus x. All right, so a little bit of elimination. So the first thing I did on elimination is I found that this one had a negative 3y. This one was regular y. So you'll see that I multiplied the top row by 3, and then I combined that with the second row. All right, and then the y's cancels each other out. So I found x was equal to 1, and then I plugged that into the top equation to find my y value. And then I did x, y minus x, because that was the fourth step. Remember, that's what the problem asked me to do. So that is if you chose elimination. If you chose substitution, you probably noticed that this y was almost by itself. You just needed to move that over. So if you did that for elimination, that would have been your first step, solving one of those for y, substituting that into the second equation, and then you'll see that you still found x was equal to 1. This one went a little faster because I just plugged that back into the purple equation. So I got y equals 4, and then you'll see you get the exact same answer when you do y minus x. So either way, it all gets you there. It's just kind of whichever method you prefer to do. So I wanted to be sure I showed you both methods depending on which way you actually did. All right, the very last thing we're going to do is take a look at how to write. We're only going to write. So we're not going to solve these yet. So this one says it's almost time for candy sales. You know what I mean. So I buy 2 pounds bag of Skittles for $3.99. And then I'm buying a 1 pound bag of Nerds for $1.99. It says I end up with 10 pounds of candy to give out and potentially snack on. And I spend $19.93. We'll see, that was before tax. It says if my daughter can guess the exact amount of each type of candy I bought, then she can have dessert before dinner. So create a system that she could use. We'll assume she's as good at math as I am. So I see 2 different equations. I see a pound equation and I see a money equation. So that's kind of how this problem is first going to work. So I also need to define some letters. So I'm going to say S is going to be the number of Skittle bags. That's kind of how many I'm looking at, Skittle bags. And then we're also going to have, I'm going to do N for Nerds. So that's the number of Nerds bags. So here's Nerds bags. Okay, so first things first, I'm going to do a money equation. So I have a $3.99 per bag of Skittles plus $1.99, and that was per bag for Nerds, gives me the grand total of $19.93. So that's my money equation. The other one is dealing with pounds. Well, I have a 2 pound bag. So 2 pounds per Skittles bag plus 1 pound bag per Nerds. So here's the 1 pound bag of Nerds. Should give me 10 total pounds. And that's my system. 2 equations to help me solve for both letters. All done. Don't have to solve. All All right, I'm gonna give you a chance to try the last one on your own and hit play when you're ready. This one is dealing with my daughter trying to build a garden, and I highlighted some keywords to help you. All right, welcome back. So here we're gonna take a look at an inequality because I'm looking at soil, which is $7.97 each per bag, and veggie seeds are $1.99 according to the local Home Depot that I Googled real quick. So it says we want at least 3 different veggies and we can't spend more than $50 on this garden. So I'm looking for all the possible ways that I could spend my money. Give me all the possibilities. So first things first, we're gonna need to define some variables. So that's what I did here. So I have S is for the number of soil, and I did V for veggies for the number of seeds. Well, I've got money, money, and money is all in green. So the first equation you'll see is my money equation. So $1.99 per veggies, and then $7.97 per bag of soil. And you'll see is less than or equal to 50 because I can't spend more than 50. So I could spend 50 or less. So I could spend $40, $30. And then the last one just says, I just only want to have at least 3 different types of veggies. So that last one, the number of veggies is at least 3. So I could do 4, 5. So that is the final equation for here. If you were curious what this actually looks like when you try to graph it, you'll see that I've got solid lines because I'm above 3 and I'm below here. So I wanted you to get a chance to see what it actually looked like when you graph it. So this one is obviously Desmos. You guys know me. So you'll see that I have veggies down here in the bottom, and then you'll see I've got bags of soil over here on the y-axis. So again, anything in these where the coloring happens for both could be possible combinations. So if I chose this one says I could do 6 veggies with 3 bags of soil. I could spend less than that. This one says I could do 14 different bags of seeds, but that's only 1 bag of soil, so don't know if I'm able to do that. Good thing is, because this line is solid, I can be equal to it. I could spend $50. So even this point on this line that says I have 13 seeds for veggies and 3 bags of soil, that would also be a solution. So I thought that one was kind of an interesting one. This is why I like inequalities. I'm a good give me all my options kind of person, and inequalities really let me see that and take that to heart. All right, we're gonna spend class time practicing a lot of these just to be sure we're really good on systems. I will see you soon. Thanks for watching.